Patients receiving artificial knees often experience pain after surgery. Pain is measured on a subjective scale with the possible values of 1 for low pain to 5 for high pain. Let Y be the pain score for a randomly selected patient. The following table gives a probability distribution for Y. Okay, so they give us a table, give us all different probabilities of patient giving different pain scores. Right, we have this one missing. Okay, so let's start out with the first one. Find the probability that a randomly selected patient, what am I doing? Find the probability that Y equals 5. Okay, so then we want to find that missing probability. Okay, so main thing that they're testing you on is just the understanding that with probability distributions, the sum of the probabilities of all possible outcomes has to be 1. So notice like these add up to 0.9 if you add these 4. So since those add up to be 0.9, this one has to be 1. 0.1, sorry. Okay, so this is 0.1. Then we'll use that for the rest of the problems. Okay, and then, so for A, probability that Y equals 5 is 0.1. Okay, so they say interpret this value. So we could say different things. You could say if you randomly select a patient, the probability that their pain score is 5 would be 0.1. You could also say 10% of randomly selected patients have a pain score of 5. So you could say it either way. Okay, so B, find the probability that a selected patient has a pain score of at most 2. Okay, so they say, so we want to do probability at most 2, so that's Y is less than or equal to 2. Okay, and all that is just adding probability of 1 and 2 together from the table. 0.1 plus 0.2, and that's 0.3. Okay, the last one they say calculate the expected pain score and the standard deviation of the pain score. Okay, so that would you use a calculator for. We'll do the whole stat thing. So here, let's do that. Okay, so if we look at the calculator, okay, first we'll go to stat and then hit enter for edit, or number 1 for edit, and then just put all the possible values for the variable into L1, and then we'll put all the probabilities into L2, the corresponding probabilities in each row. Okay, and then we'll go back to stat, and then go to calc, and that's what we want, one variable stat. And then just make sure you, okay, and then just go down to calculate. Oops. So just showing where it is, second 2 is L2. Okay, and then there's all the numbers. Okay, so expected pain score. So the expected pain score is really the same thing as the mean. So expected pain score, for Y is the mean of Y, which is the 3.1. X bars is mean. And the standard deviation is just given. They say standard deviation of X, but 1, 6. Okay. Okay, and that's it for this. Okay, next one, in a process for manufacturing glassware. Glass stems are sealed by heating them in a flame. Let X be the temperature in degrees Celsius for a randomly selected or randomly chosen glass. The mean and standard deviation of X are 550 degrees Celsius and 5.7 degrees Celsius. Okay, for A, is the temperature discrete or a discrete or continuous random variable? Explain your answer. Okay, so this is definitely continuous. If it's temperature, things like temperature that are measurements are almost always continuous. Maybe some rare cases are discrete. But you can see, temperature could be any value. Even if you pick two random values, 0 and 1, there's an infinite number of temperatures in between 0 degrees Celsius and 1 degree Celsius without any gaps. There's just an infinite number of values. So definitely continuous. Okay, B. The target temperature is 550 degrees Celsius. Okay, what are the mean and standard deviation of the number of degrees off target, which you could represent by D, which is X minus 550. Okay, so just notice kind of what they're saying here. And they didn't have to give you this formula. They could have made you come up with this. But that makes sense. Like if the target's 550, whatever your actual temperature is, to figure out how far off target it is, you want to subtract 550. So like let's say your target is 550, but you get 560, right? If X is 560, then if you subtract, you get 10, and that makes sense. You're 10 degrees off target. If it's 540, you get negative 10, and so like the positive and negative values tell you if you're off target by being above the target or being below the target. Okay, so just to kind of understand what this is and what they're talking about. Okay, so they say what are the mean and standard deviation? So the mean of D is really whatever. Anytime you add or subtract to a distribution, that affects the mean, and multiplication affects the mean also. So everything affects the mean. Any kind of measures of center get affected by addition and multiplication. So this will be the mean of X minus 550, and that was 550. Okay, and then the standard deviation of D. Okay, standard deviations don't get affected by addition and subtraction, so it's just the standard deviation stays the same. Okay, and then for C, they say a manager asks for results in Fahrenheit. The conversion of X into degrees Fahrenheit is given by that formula. What are the mean and standard deviation of the temperature of the flame and Fahrenheit scale? Okay, so notice this formula involves multiplying the random variable X by something and then adding something. Okay, since the mean gets affected by both, we'll do both to the mean, but since the standard deviation only gets affected by multiplication, we won't add 32 at the end. Okay, so it'll look like this. So the mean of Y so that ends up being 1022. Right, and then the standard deviation of Y is just 9/5. Standard deviation of X. Standard deviation of x was 5.7. And that ends up being 10.26. Okay, so this one kind of had to deal with a lot of the concepts of when to multiply or add or subtract or divide when you're doing that to a random variable to get another random variable. So in a game of 4-spot Keno, the player picks 4 numbers from 1 to 80. Casino randomly selects 20 winning numbers from 1 to 80. The table shows the possible outcomes of the game and their probabilities, along with the amount of money, the payout that the player wins for a $1 bet. If X equals the payout for a single $1 bet, you can check that the mean of X is 70 cents and the standard deviation is 658. Okay. So we could do that. We could put these in, put all these values. First off, these 0 through 4. These are like categorical variables, so these you don't do any kind of math with. So it's really just the payouts and the probabilities that we would be analyzing to find like mean and standard deviation, things like that. Okay, so we could put like the payouts into L1 and all these probabilities into L2, do one variable stats, and it would give us whatever the mean and standard deviation that they said. Okay, let's start. So first, they say to make a graph of the probability distribution. So I just took that from the solutions, and notice kind of the main thing to notice is the values of the variable go on the bottom. The fact that we had 2 payouts that were the same, and those are 2 possible values of X that are the same. They occur for different matches, but they're still the same outcome. So you can just do one, if you're going to graph it, you can just do one bar and add up the probabilities for that particular outcome, and then you get this big bar. So if you add these together, you get something a little bit bigger than 0.7, and that's why this bar is a little bit higher than 0.7. Okay, and then the rest of the payouts just had one chance of happening, and so we can make a bar for each of those. And then notice, so there's 0, 1, there's a little gap for 2, there's not a payout of 2, then they have a payout of 3, and then notice they did this little break in the graph type of symbol, and so this just tells you that there's a break in the graph. It's almost like a dot dot dot, and then you have 120 way over here. You don't want to do a graph that includes 4, 5, 6 all the way to 120 just to have a 120 way out there. So okay, so that's just good to know that that's one option if you're making these graphs with huge gaps in the X values. Okay, when they say describe what you see, they mean describe the distribution. This is a distribution. So we'll do, SOCV. So this is definitely skewed right. Okay, give the mean, give the standard deviation, the shape, maybe mention that there's an outlier, I guess, that 120 is a definite outlier. 120 outlier, and then just give whatever they said the mean and standard deviation was. Is 70 cents and standard deviation is that 658. Okay, so that's describing the distribution. Okay, so here I'll do B over here. So they say interpret the values of the mean and standard deviation. So this would be like the mean would be like if you made, you know, many bets, many $1 bets, the average payout for each of those bets would be 70 cents. So actually I'm not going to write this, I'm just going to say it. So that would be interpreting the mean. The standard deviation, you'd say same thing. If you made a large number of $1 bets, the payouts would typically vary by $6.58 from the mean of 70 cents. Okay, so that's B. Okay, for C, Jerry places a $5 bet on 4-spot Keno. Okay, so find the expected value and the standard deviation of winnings. Okay, so this one is just all of these payouts were for a $1 bet. So really everything just gets multiplied by 5. All these X values get multiplied by 5. Okay, so that means that we'll let Y be the expected value for a $5 bet. Okay, and then we could say the mean of Y is really 5 times the mean of X, which is and then the standard deviation of Y. So standard deviation is affected by multiplication, so this will get multiplied. Whoops. Okay, that ends up being $32.90. Okay, for D. Okay, so Maria plays 5 games of 4-spot Keno, betting $1 each time. Find the expected value and standard deviation of her total winnings. Okay, so and this problem is kind of showing you the difference between making a $5 bet or 5 $1 bets. They're not the same thing. At least they are the same in some ways, but not the same in other ways. So first, just to see exactly what's going on, you're reaching into this distribution 5 different times. You're playing 5 different games, so you're going into this distribution 5 different times, which is different than just increasing all these bets by a multiple of 5 and then just playing once. In that case, you're just going into the distribution 1 time still. But here for D, we're going into the distribution 5 different times, and so technically we'll be doing this. So like we'll say we'll make W. So let's just say W is the payout for all 5 bets, all 5 $1 bets. Okay, so that means like W is the payout for the first one plus the payout for the second one plus the payout for the third one, payout for the fourth one, just to see what's going on. So this is different than just multiplying by 5. Yeah. Okay, so technically, like if we were going to find the they want to find the expected value, which is the mean. So the mean of W is technically like the mean of X plus the mean of x. But that's really just 5 times the mean of x. Okay, so that ends up being the same as if we had just placed a $5 bet. And that should make sense. Okay, now, if you're finding the standard deviation, though, you can't just multiply. Remember, you can't multiply or add to the standard deviation when you're dealing with more than one distribution, like in this case. So now the distribution, the W, is really, or the standard deviation for W, is really the square root of all their variances. So this would be like the variance for x plus the variance for x variance. And so remember, variance is just standard deviation squared. Which is really just square root of 5 times the variance of x. Okay, and then now we can just do that in a calculator. Do this. Okay, what was the variance for x? 6.58. Okay, and then whatever that ends up being, 14.71. $14.71. Okay, so notice we can't just multiply by the standard deviation by 5 in this case like we could with the other one. You have to be adding their variances and then taking the square root. So, okay, machine fastens plastic screw-on caps onto containers of motor oil. If the machine applies more torque than the cap can withstand, the cap will break. Okay, both the torque applied and the strength of the caps vary. The capping machine torque T follows a normal distribution with mean 7 inch-pounds and standard deviation 0.9 inch-pound. The cap strength C, the torque that would break the cap, follows a normal distribution with mean 10 inch-pounds and standard deviation 1.2 inch-pounds. Okay, let's highlight, I like the highlighting thing. So this is 2 different distributions. So they say cap machine, so like the torque T, mean of 7, of 0.9, and the cap strength C, mean of 10. Okay, so that's going to be pretty much everything we'll need in the whole problem is highlighted. So. Okay, so the first one, first part A says find the probability that a randomly selected cap has a strength greater than 11 inch-pounds. Okay. So first, they say it's a normal distribution. So, and they ask for a probability. So anytime the question asks for a probability of a normal distribution, almost always, if not always, you'll do normal CDF. Okay, so yeah, so here let's go to, so we'll go to the calculator. So we'll look down at the calculator. Do second VARs distribution number 2. Okay, and since actually here, let me do this real quick. So we want to find probability greater than. So the cap strength C has a strength greater than 11. Okay. So it makes sense that the lower should be 11 and the upper will be just some big number. So, okay, so let's go back to the calculator. Okay, and then we'll put in the mean was 7 and the mean was 10, sorry for this one. And then standard deviation 1.2. Okay, paste and then hit enter. Okay, so my advice, especially on if it's an FRQ that you did all in the calculator like this, at least put like what's showing on the calculator right before you hit enter. Okay, and then part B says, explain why it's reasonable to assume that the cap strength and the torque applied by the machine are independent. Okay, so reasonable to assume they're independent because they're two totally separate machines. You know, there's one machine that makes the cap, and so that'll determine the cap strength, and there's a totally different machine that actually applies the torque. And they're just separate machines, so the outcome of one is unlikely to affect the outcome of another, so I think. Okay, part C. Let the random variable d equal c minus t, and then find the mean and standard deviation. Okay, so this is subtracting two distributions. Okay, the distribution of cap strength and the distribution of torque. So first, think about what this variable d represents. You know, actually, we'll talk about that in a second. We'll talk about that for part D. Let's just find this. Okay, so the mean of D, when you're subtracting two distributions and you want to find the mean of the resulting distribution, just subtract the means of each distribution. So it's kind of, measures of the center are kind of easy. Okay, the mean of C was 10. The mean of T, 7. This will be 3. And inch pounds. Okay, so that's straightforward, but the standard deviation is different when you're adding or subtracting two or more distributions. Okay, you can't just add or subtract their standard deviations, so you have to do this thing where I guess we did that in another problem, but we'll do it again. So we can add or subtract variances, really add variances. So even though this is subtracting, we're going to really add the variance of each. Okay, and then the variances are 1.2 and 0.9. Equals, I'll do it in the calculator, 1.5. Okay, last one talks about what's the probability that a randomly selected cap will break while being fastened by the machine. Okay, so they're not always going to tell you exactly what to do. You have to think about in context, what to do. So think about a cap will break if the torque applied is stronger than the strength. right? And they define it up here. Cap strength is the torque that would break the cap, right? So if the torque being applied to the machine is higher than the torque that would break the cap, then it'll break. So we really want to figure out what's the probability that the cap strength is less than the torque being applied to it. Or another way of saying that, remember we could take the t and subtract it to the other side, just using algebra. We could write this as probability of c minus t being less than 0. Okay, and this is really c minus t is what we're calling d. So it's really probability d is less than 0. Okay, and the whole point of doing that is you can't do in the calculator what's the probability that something's greater than something else, but you can do probability that a distribution is greater than or less than some number. So okay, so we'll we'll end up doing, so if you add or subtract two normal distributions, you get a normal distribution. So this d is normal. So when we're finding the probability, we'll do normal CDF again. We'll make the lower some small number, and then the upper 0, and then we've got our mean and standard deviation. And so now we'll go to the calculator for the rest. Okay, so remember normal CDF second vars, and it's number 2. Okay, make the lower some big negative. Doesn't matter. It's always a big number relative to the standard deviation and the mean. Upper 0, and then 3 was our mean, and 1.5 was the standard deviation. Alright, and that's it. And actually, let me do this before we give the answer. I will say this is normal CDF. Okay, so that's better, kind of, if you're doing an FRQ to show work. So you can at least get partial credit if you make a mistake, some little mistake. According to Mars Incorporated, 20.5% of the M&M's milk chocolate candies made at its Cleveland factory are orange. Assume that the company's claim is true. So we'll always do that, always assume that the claim is true when we're doing this statistical analysis. So suppose you take a random sample of 8 candies from a large bag of M&Ms. Let x equal the number of orange candies you get. Okay, so x is the number of orange candies you get out of a sample of 8. Okay, explain why it's reasonable to use a binomial distribution for probability calculations involving x. Okay, so for A. Anytime you want to answer this question, always the same. To say why it's a binomial distribution, always start off with doing bins. Okay, we'll go through each one. So is it binomial? When you're choosing these candies from this sample, to get this sample, is there a success or failure? Yes. Getting an orange or not getting an orange. So it passes that. Okay, is getting each candy, let's see, hold on. Yeah, so they say you take a random sample of eight candies from a large bag. Okay, and so this idea of them talking about a large bag is significant. So the fact that it's technically not independent because um, you're choosing eight candies. So let's say you choose the first one. If it's orange or not orange, whether or not it's orange will affect the probability of you getting an orange on the second try, right? If you get an orange on the first try, on the first picking, there'll be less oranges, right, and one less total, and so that'll affect the probability of the next one. Um, so definitely not independent. Okay, but let's see if it passes the 10% condition. Okay, so the sample size, compare that to 10% of the population. Okay, so in order for it to pass the 10% condition, this large bag just has to be more than 80, right? If the large bag it was 80 or more, then this 8 would be less than or equal to 10% of the population. So I think we'll assume that there's more than 80 M&Ms, and if they talk about there's a large bag. So okay, so we're going to say it doesn't pass the independent, but it does pass the 10% condition. Okay, and then go to the n and bends. So is there a fixed number of trials? Yeah, so the sample size is the number of trials, so that's 8. And it's not the same probability every time, but passing the 10% condition accounts for that, makes the approximately the same probability every time. Okay, and so that's why it's reasonable to assume that it's a binomial distribution, because it doesn't technically pass bends, but it passed the B and N, so it always has to pass that. And then even though it didn't pass the I and the S, independent and same probability, the 10% condition can make up for that to say that it's approximately binomial, and then we can use binomial distribution for assume that it's a probability distribution when we're doing probability calculations. Okay, so that's A. Okay, B. What's the probability that you get 3 orange M&Ms? Okay, now that we've established that it's approximately binomial, we can use binomial PDF. So we want to know what, first of all, notation-wise, this is x, probably that you get 3 oranges, probably that x equals 3. Okay, so we'll do that in the calculator. Okay, so do second vars, distribution, go all the way down, not all the way down, but no, PDF is A. Our trials was the same as the sample size always, if there is a sample. Probability is 0.205, 20.5%. And we want to know probability of getting 3. Okay, so we'll say that's, oops. Okay, for C, calculate probability x is greater than or equal to 4. Okay. So, we'll ultimately be doing binomial CDF, but binomial CDF can only do less than or equal to. So if we want to find greater than or equal to, we'll be doing 1 minus. Okay, we really want to know what's the probability, the kind of the opposite of greater than or equal to 4, is it less than or equal to 3? Okay, so that's what we'll do. We'll do binomial CDF in the calculator. So we'll go to the calculator. We'll do binomial CDF and just make sure our x value is 3. do 1 minus second vars. Well, then binomial CDF. Okay, all this is the same actually as the last one. All right, and that's it. And then D. Suppose that you get 4 orange M&Ms in your sample. Does this result provide convincing evidence that Mars's claim about M&Ms is false? Okay, so remember, if we assume the claim is true and we get a sample result that is really unlikely, assuming that the claim is true, then that's evidence against it. So we'll test to see, and we'll always want to know, they say the sample you get 4 orange, so we want to know 4 or more extreme. I think more extreme would be greater than 4 because it's already unlikely. If you had a bag of 8 candies and there's a 20% chance of getting an orange, 20% of 8 is less than 2. So that would be the expected number of orange candies, around 1 or 2. So to get 4 is already higher than that, so more extreme is greater. So we want to know what's the probability of getting, so we already did that. Yeah, so of getting greater than or equal to 4. Okay, and so that's why we already did that. So we found that probability is 0.061. And so with the way we do it, if this is, this is our p-value. If this was less than 0.05, then we say that there is convincing evidence. But, the question says, does the result provide convincing evidence? And so we'll say no, since our p-value 0.061 is greater than 0.05. We do not. Seeing evidence. Mars's claim is false. Okay, so that was something that we did a while ago, and that'll come back a lot, that 0.05 convincing evidence thing. Okay, so the next one's pretty quick. They say, this is dealing with the same setting. So they say find and interpret the expected value of x. So for binomial setting, the expected value is the mean. And it's really just the number of trials, or the sample size, times the probability of a success. The size was 8. And then probability is 0.205, 20.5%. Okay, we're doing a calculator. This is 1.64. Okay, and then the interpretation would be as if you selected many random samples of size 8, basically just replicated this situation, we would expect to get about 1.64 orange M&Ms on average. Okay, B. So the standard deviation has just a different formula for binomial setting. So I'll do the formula is n times p times 1 minus p, and then square root that. That would be 8 times 0.05. So it starts off the same as like the expected value, and then you just kind of times it by 1 minus p, which would be 0.795. Okay, and that ends up being 1.14. Okay, so we just needed to use those formulas. And then interpreting, so you'd say if we were to select many, many random samples of size 8, the number of orange M&Ms would typically vary by about 1.14 orange candies from the mean of 1.64. So something like that. Okay, in the Japanese game show Sushi Roulette, the contestant spins a large wheel that's divided into 12 equal sections. 9 of the sections show a sushi roll, and 3 have a wasabi bomb. Okay, when the wheel stops, the contestant must eat whatever food applies to that section. Then the game show host replaces the item of food on the wheel. To win the game, the contestant must eat 1 wasabi bomb, so it has to land on wasabi just 1 time. Okay, let y equal the number of spins required to get a wasabi bomb. Okay, part A. Find the probability that it takes 3 or fewer spins for the contestant to get a wasabi bomb. Okay, so first off, in order to find probability, we have to know what type of probability distribution is this. Is this one where we'll make a table and then multiply, and then add, to get the expected value? Is this a binomial? Is it geometric? Is it normal? Right, because each case we'll be doing a little different calculations. Okay, so this one is geometric. Okay, we can do bits real quick. Okay, so you win by it landing on wasabi bomb. So this is definitely binary because it either lands on wasabi bomb or doesn't. Okay, independent, yeah, because the wheel makes it like a random, random thing every time to what it lands on. And then bits is trials until a success, and that's what this is. You're going to keep spinning until you get a wasabi bomb. That could be on the first one, it could be on the 10th one. You could get 9 sushis in a row, and then the 10th one is a wasabi bomb, and so that passes the T. And then kind of for the same reason that it passes I, it's the same probability every time of it landing on a wasabi bomb, which is really 3 out of 12 or 1/4. So okay, so they say find the probability that it takes 3 or fewer spins for the contestant to get a wasabi bomb. So for A, the probability that y is less than or equal to 3. Okay, 3 or fewer. So that's going to be geometric CDF. Okay, so we'll go to the calculator. And geometric, you only have to type in 2 things. We'll do second vars, and I'll hit up for geometric because it's, the thing on the very bottom. If you hit up, it goes to the bottom. So the probability is 0.25, right, since it's 3 out of 12. And we want to know less than or equal to 3, so we'll put 3, and that's it. Okay, if we were showing our work for an FRQ, okay, so for the next one, they say find the mean of y. So for geometric, you want to know the mean of y. Oops. Okay, so mean is just 1 all over p, and these formulas will be given. Okay, probability of success, so it's 0.25. And so this ends up being 4. Okay, and so this would be 4 spins. Okay. That makes sense, I think. If it, if one out of every, if there's, one out of every four sections is a wasabi bomb, makes sense. It'll take 4 spins on average. Okay, anyways. And then to interpret this, you'd say something like, if this if the wheel was spun many times, the average number of spins it would take to get the first wasabi bomb is 4 spins, something like that. Okay, and then standard deviation. So the formula for that is a fraction, square root p over p. Okay, p is 0.25, so this is square root of 0.7525. And that ends up being 3.464. Okay, and then to interpret this, you'd say something like, if the wheel was spun many times, the number of spins it would take to get the first wasabi bomb would typically vary by about 3.464 spins from the mean of 4 spins. In a large city, 34% of residents use public transportation at least once per week. Suppose the city's mayor selects a random sample of 200 residents. Okay, let T equal the number in the sample who use public transportation at least once per week. All right, what type of probability distribution does T have, and justify your answer. Okay, so it seems like it would be binary because we're taking a sample, so that's like a sample of 200. Actually, let's go through bins real quick. So it passes n since there's 200 in the sample. It's a binary. It's binary because you either select a resident. As you're selecting the sample, each person you pick for the sample could either be someone who uses transportation at least once per week or doesn't. That's what we're interested in. Okay, and then the fact that we're selecting a sample, when you're selecting people, you're not replacing them and then selecting someone else. So it won't pass independent, which means it technically won't pass the same probability condition. But let's see if it passes 10%. So the fact that they say... The fact that they say at the very beginning it's a large city. Okay, so that implies that there's more than 2,000 people in the city. So we can say that 200 is less than or equal to 10% of the population in that city. And notice, as long as the population is greater than 2,000, this will be true. So we're assuming that is true. So it passes a 10% condition. So we can say it's approximately binomial. Okay, for B, explain why T can be approximated by a normal distribution. So it's approximately binomial. So if something's a binomial or approximate binomial, and then let's see if it passes the law of large counts. If it does, we can approximate it by a normal distribution. If not, then the farthest we can do is say it's approximately binomial. Okay, so the law of large counts is n times p, sample size, times probability of success, and n times 1 minus p, which is sample size times probability of a failure, has to each be greater than or equal to 10. Okay, and another way to look at this is the expected number of successes, and this is the expected number of failures. So those have to both be greater than or equal to 10 in order to pass law of large counts to say that the distribution is approximately normal. Okay, so the probability of success is 0.34. Whoops, or the sample size we'll do first is 200. And then for failure, it'd be 0.66. Okay, so this is 68. And this is 132. And these are each greater than or equal to 10. Okay, so we can say it's approximately normal. Okay, and then part C. So now that we've established that it's approximately normal, now they say for part C, calculate the probability that at most 60 residents in the sample use public transportation at least once per week. Okay, so we want to say what's the probability that T is, they say at most 60, so T is less than or equal to 60, at most 60. Alright, so this is a normal, and we want to do like less than or greater than something. We'll go to the calculator and do normal CDF. Let's go back to the calculator, second bars, do normal CDF. Less than 60, so we'll keep that. That's just a really small number. We can keep that like that. Make the upper 60. Okay. Oh, so we don't have the mean or standard deviation, right? Oh, I forgot about that. Okay, so let's find both. Okay, so since this, neither are given, and they have to be given for a normal distribution, but the fact that it's approximately binomial, we can use the formulas for binomial. So for binomial, we could say it's n times p for the mean, which is 200 times 0.34, which is 68. And then the standard deviation is square root of n times p times 1 minus p. Okay, and I'll do that in the calculator, and that ends up being 6.699. Okay, so let's go back to the calculator, and we can put those in now. Alright, and that's it. Just do negative 1,000. It'd give us the same answer, 60. Okay. Okay, so the FRQ at the end, they say Buckley Farms produces homemade potato chips that it sells in a bag labeled 16 ounces. Total weight of each bag follows an approximately normal distribution with a mean of 16.15 ounces and a standard deviation of 0.12 ounces. If you randomly selected one bag of these chips, what's the probability that the total weight is less than 16 ounces? Alright, so this is a normal distribution, and they want to know if just selecting a single bag what's the probability that it's less than 16 ounces. So we'll do normal CDF, and we'll make our, let's probability, we'll call this distribution X. Okay. And then we'll say probably less than 16 ounces. Okay, and so X is the weight of the potato chips or single potato chip bag. Okay, so let's go over to calculator, do normal CDF, second bars. Okay, so that's fine for the lower, some super small one. That's 16, and then they gave us the mean and standard deviation. .12. Okay. Okay, part B. If you randomly selected 10 bags of these chips, what's the probability that exactly 2 bags will have a total weight less than 16 ounces? Okay. So now the last one was normal since we were just selecting one bag, but here we have something different, right? If you randomly selected 10 bags, so we have like a sample now. So in that case, that's like a number of trials. They say the probability that exactly 2 of the bags, so we want to know like a certain probability and have a total weight less than 16 ounces. So as we're selecting these bags, there's a success and a failure. Weighs less than 16 ounces or doesn't weigh less than 16 ounces. So this is a binomial setting, so we can use binomial PDF. And they say exactly 2, so that's PDF. Okay, so we'll go to the calculator. So do second distribution again. Go all the way down to A. PDF. Number of trials was 10. That's the sample size. Success was our p-value from the last time. Put in the exact value. And then our x value is 2. Okay. So notice we had to use the probability from the previous problem because that is the probability that a single bag weighs less than 16 ounces, and that's our probability of success. Weighing less than 16 ounces is our success, so that's the probability of success. So we should have said that. So we'll say the probability, oops. Let's say, call this y, call it something different. So we'll say y. The last one was a normal distribution, just selecting one bag. This is a binomial distribution because this is a binomial setting now. So we'll have to call it a different variable. So we want to say y equals 2. So this is Okay, part C, same setting. They say Buckley Farms ships its bags in boxes that contain 6 bags. The empty boxes have a mean weight of 10 ounces and a standard deviation of 0.05 ounces. Calculate the mean and standard deviation of the total weight of a box containing 6 bags of chips. Okay, so we'll call this new distribution maybe Z. so we want to find calculate the mean and standard deviation. So we want to find the mean of z, which is just the mean of all the different means added together, you know. And technically, you know, so there's 7 different things that are all being added together, and each one comes from a different, you know, the box comes from the distribution of all possible boxes, right? They have a little variation in the weight, but on average they're 10 ounces, a little bit more or less. And then each bag comes from the same distribution, but they're still selected one at a time, you know, from different, you know, it's almost like they're from different distributions. So we'll say this is the mean of the box plus the mean of each of the bags of chips. So this will be the mean of x plus mean. And I'm just showing work. If there's more, I wouldn't do this, but it's not that many. Oops. Okay, is there 6 of those? Yeah. Okay, so that's really just the mean of the box, which was 10, plus 6 times the mean of the bags of chips, which was 16.15. Okay, if we do this in the calculator, this ends up being 106.9. And this is ounces. Okay, and then the standard deviation, Z is a little different. So we'll do the standard deviation of the box squared, because we'll do variance. So we'll really add up all their variances. And this one I won't write them all out, but really you'd write out the same way. You'd write out variance squared, you know, or variance. But I'm just going to do 6 times the variance of the bag of potato chips. So the standard deviation of the box is 0.05. 6 times standard deviation of the bags of potato chips is 0.12. Okay, if you do that in the calculator, you get 0.298 ounces. Okay, and then the last one. Part D says Buckley Farms decides to increase the mean weight of each bag of chips so that only 5% of the bags have weights that are less than 16 ounces. Okay, assume that the standard deviation remains 0.12 ounces. What mean should Buckley Farms use? Okay, so you know, the fact, if you want to like find the mean or standard deviation, let's say, we'll use like that z-score formula. So let's bring this back. So value minus mean over standard deviation. Okay, so remember the z-score is associated with the percent. You know, just to kind of remind, you got this normal distribution, and then this is some kind of z-score. And there's a z-score associated with 0.05. So with that area equals 0.05, there's some z-score associated with that. Okay, that you can find from table A. Or you can do inverse norm and just make the mean and standard deviation 0 and 1. But I'm just going to do from table A. And if you find it from table A, the z-score ends up being negative 1.6, say 4 or 5. It's like right in the middle of 4 and 5. So, okay, so that's our z-score. Okay, so we wanted 5% to be less than 16 ounces, so 16 is our value. Try to find the mean, and they said that the standard deviation is the same. Okay, so just solve this for mean, just a little algebraic equation, and you get mean equals 16.197.